Welcome to Research Edutica. Today we are going to talk about Professor Eisenberg and streamline the self-assembly of block copolymers. He's professor at McGill University and expert of ion-containing polymers. Before starting this lecture, please feel free to check our courses that I will post on Udemy about supramolecular chemistry, where you will have all the details. And before starting with presenting the work of Professor Eisenberg, I'm going to present you a background about polymer chemistry and self-assembly of block copolymers. Self-assembly is a spontaneous organization of components. Self-assembly is a cornerstone of life because most of the biomolecules can self-assemble in three-dimensional spatiotemporal organization. Different polymorphs can be observed under thermodynamic control, kinetic control, and also non-equilibrium systems. Hierarchical self-assembly are driven by consecutive assembly levels on pathway. Self-assembly is driven by non-covalent interactions, such as hydrophobic, metal ligand, dipole-dipole interactions, pi interactions, hydrogen bonding, van der Waals interactions, steric interactions, electrostatic interactions. Self-assembly is finally the result of cooperative and non-cooperative interactions. Different polymorphs could be obtained with one block copolymers, such as micelles, inverted micelles, rods, bilayers, vesicles, lamellae. At least 30 polymorphs have been reported in the literature. In summary, self-assembly is due to non-covalent interactions. It follows dissociation pathways. Different polymorphs can be obtained depending on the condition, under thermodynamic control, kinetic control, and for non-equilibrium systems. So for one chemical structure, and depending on the experimental condition, different polymorphs could be obtained. Block copolymers are generally prepared by bottom-up technique. Amphiphyte copolymers derive from two or more different monomers. One portion is hydrophobic, such as block A. One portion is hydrophilic, such as block B in the figure. Block copolymers are characterized by their TG, the glass temperature transition, giving information about the stretching between the chains. Also by their volume fraction of the block A and the block B, Fa and Fb. And the aggregation process is characterized by the critical micelle concentration, the concentration of amphiphyte molecules above which they start to self-assemble. The degree of incompatibility between the blocks A and the blocks B is defined by the Flory-Huggins interaction parameter, Ca. The equation for block copolymer is in the right side, where Z is the number of nearest neighbors per repeat unit in the polymer, Kb the Boltzmann constant, Kbt the thermal energy, epsilon AB, epsilon AA, and epsilon BB represent the interaction energies per repeat unit of AB, AA, and BB, respectively, and N, the aggregation number. When N equal 1, it's a monomer. When it's a dimer, N equal 2, number of molecules per aggregate. If you multiply CAB by N, you have information whether it is an orthophilic molecule that can self-assemble. If CAB multiplied by N is above 11, 10, 11, it's an orthophilic molecule that can self-assemble into aggregates. The Gibbs free energy of the self-assembly process is represented by this equation. The Gibbs energy depends on the number of mole of Na and the number of mole of Nb, and also depending on the Floor-Higgins parameter. For N molecules of block copolymers, each aggregate is characterized by the constant equilibrium constant and the chemical potential. Each aggregate is characterized by the concentration of molecules in aggregate N, by N, the aggregation number, and the chemical potential in aggregate N. The ratio of concentration of molecules in aggregate N by the aggregation number gives you the concentration of aggregate N, and the energy per aggregate equal number, the aggregation number multiplied by the interaction self-energy per molecule. At equilibrium, all molecules have the same chemical potential. And at equilibrium, the equilibrium constant is defined by the association constant divided by the dissociative constant, which is exponential to the delta G divided by the KBT, the Boltzmann constant, the Boltzmann equation, sorry. And the formula A gives a relationship between the equilibrium constant and the chemical potential in aggregate N. The rate defines the dissociation pathway. The rate of association equals Ka multiply x1 to the square of n. The rate of dissociation equals Kd multiply the concentration of molecules in aggregate N divided by the aggregation number. At equilibrium, we have this equation where the rate of association equals the rate of dissociation. Finally, by using the equation of the equilibrium constant, K equals Ka divided by Kd, and the fact that the rate of association equals the rate of dissociation, we get a relationship between the concentration of molecules in aggregate N and the aggregation number, as displayed in the equation surrounded by the right rectangle. By drawing the concentration of molecules in aggregate N with the aggregation number, we can find the maximum and aggregate NAGG, which represents the highest number of molecules per aggregate. In our courses on Udemy that we will post from the end of February, March, we will spotlight the importance of the thermodynamic control and the equilibrium assemblies, how to get kinetic assemblies, and how to define non-equilibrium dissipative or non-dissipative assemblies. All these processes are very important to predefine the nature of the polymorph. Please have a look to our courses to have much more details. For the analysis of block copolymers, different techniques can be used in parallel. For the dynamic process, it's always important to understand the dynamic of the self-assembly. To get some ideas about the dynamic assemblies, it's always important to define and to find the kinetics of the process. For example, with using the laser temperature jump spectroscopy, time resolved small angle X-ray, neutron spectroscopy, variable temperature, UV, Vis, fluorescence, and find the OBT model and the hysteresis. Using the UV visible spectroscopy, the fluorescence, photoluminescence, NMR, microscopy, TEM, SEM, AFM, DLS, circular dichroism, small angle X-ray scattering, EPR probes, neutron spectroscopy, to find the dielectric properties with the zeta potential. And as I have said, always study the kinetics and find the key constant and parameters. In summary, we have learned how to define and amplify block copolymers by multiplying the Flory-Huygens parameter by the aggregation number. If this number is over 11, we have 10, 11, we have an amplified block copolymers. Other parameters are important to define the equilibrium process, the Gibbs energy, the chemical potential, and the equilibrium constant, which all define the assembly process. Study always the kinetics of the process to have some information about the thermodynamic. Professor Eisenberg was born in Poland. He is a very famous polymer chemist who has pioneered the study of ion-containing polymers. We are going to present how he has streamlined the self-assembly of block copolymers with one of his reviews, the Chem review, published in 2012. You can have more information about his life and how he has developed all these important processes for chemistry in the publication published in 2000 in the journal Micromolecules. Professor Eisenberg has focused the study of the relationship between the structure and assembly of block copolymers by using block copolymers, polystyrene, block polyacrylic acid. He studied in depth all the process of a self-assembly. He described with this polymer, block copolymer, different polymorphs such as spherical micelles, cylindrical micelles, bicontinuous structures, lamellae, toroids, and vesicles, and so on. He reported almost 30 polymorphs of these block copolymers. He studied the structure-assembly relationship by controlling the thermodynamic and the kinetics by using the polystyrene block polyacrylic acid block copolymers. You can notice that the polyacrylic acid is negatively charged, and he tuned the chemical structure of this block copolymer to see the effect on the structure-assembly relationship. Other parameters that can affect the structure-assembly relationship is the process of preparation, the concentration effect, the solvents effect, the addition of ions, the addition of homopolymers, the size hybridization, the study of the thermodynamic versus kinetic control. He emphasized the importance to study the chemical structure of the block copolymers, whether you have a diblock, a triblock, mixto arm, alternating blocks, tapered blocks, and so on. He emphasized the importance to determine the volume fraction of the blocks A and B, to determine the total degree of polymerization, to determine the degree of incompatibility between the blocks A and B by calculating the product of the psi AB, the fluorines, by multiplied by the aggregation number. We said before it should be higher than 10, 11 to define it as the amphiphilic block copolymers. Also to determine the order to disorder transition temperature, TODT. With the study of the block copolymers polystyrene polyacrylic acid, we got different polymorphs, and mainly we got the spherical micelles, the rods, bilayers like lamellae and vesicles, hexagonally packed hollow hoops structures, large compound micelles with inverse micelles, LCMS. 3 parameters are extremely important to study the relationship structure activity of block copolymers. It's very important to keep that in mind. I need your attention. It is the degree of stretching of the core forming blocks, the interfacial tension between the micelles core and the solvent outside the core, and the most important is the repulsive interaction among corona forming chains. This is the most important one. They are characterized by the number average core radius, the degree of stretching of the polystyrene chains of the core, the area per corona chain on the core surfaces, AC. This AC is very important to determine this repulsive interaction. I said that this repulsive interaction is very important to determine the curvature of the aggregate and the nature of the self-assembly. As a reminder, 3 parameters are important to define the relationship structure assembly of block copolymers. R core, the number average core radius, SC, defining the degree of stretching of the polystyrene, AC, the surface area per corona chain at the core corona interface calculated from the dry aggregate. This parameter AC is very important to determine the curvature at the corona core interface. We have emphasized to determine the volume fraction of block A and block B. When the volume fraction of block A is small, there is a high curvature at the interface of the corona and the core. We get sphere. Upon increasing the volume fraction of block A, we can shift from sphere to cylinder. Then when the volume fraction of B is close to the volume fraction of A, the interface is flattened and we get lamellae. Frank Bates reported this scheme where on the left, when the volume fraction Fa is small, we get spherical micelles. At the beginning, while preparing aggregation, we always start with spheres. Upon increasing the volume fraction of Fa, we shift from spherical micelles to rods Then, upon increasing the volume fraction of A, we shift to bicontinuous rods, small and large lamellae, vesicles, hexagonally packed hollow hoops, until getting large compound micelles with inverse micelles when Fa is close to 1. Professor I.D. Eisenberg tuned the chemical structure of his polystyrene block polyacrylic acid, and he got different polymorphs such as spherical micelles, rods, bicontinuous rods, small lamellae, large lamellae, vesicles, and even large compound micelles. He emphasized the importance of the repulsion between the chain of the corona, which creates some interfacial forces that determine the shape of the aggregate and the curvature on the surface. Regarding the process, he described different processes for the preparation of the self-assembly aggregates. The hydration approach for the preparation of giant vesicles, the electroformation, the layer by layer assembly, microfluidic techniques, and the nanoprecipitation process, which is one of the most important. In the precipitation process, we take a beaker and we fill the beaker with an organic solvent such as DMF, dioxane, DMSO, or THF, and we add the amphiphilic compound. Then we add dropwise or directly water, 25 to 50% content. You can imagine inverting the order of addition to get kinetically trapped species. For example, you had your, like described in the right side, you can mix your block copolymer in water and then add your organic solvent, DMF, dioxane, DMSO, or THF. Then you proceed with the dialysis for the purification of your block copolymer assembly. For spherical micelles, when the aggregation number increases, the core size increases. One more thing, the curvature at the interface corona core is higher, which explains the fact that we got spheres. As a reminder, the interchain repulsion of the corona between the corona chains is the most important parameter to determine the nature of the self-assembly. Regarding the concentration effect, the aggregation number is a function of the copolymer concentration, as described in this equation. The aggregation number, when the aggregation number increases, the core size increases. It means when the concentration increases, the core size increases as well. Regarding the solvent effect, copolymers always form spherical micelles at the early stage because they are the kinetically trapped nucleates. Upon increase the water content until a certain limit, it shifts from spheres to rods, then vesicles. Regarding the co-solvent effect, solubility parameter and the dielectric constant of the blocks and solvent are very important. For example, by using block copolymers, polystyrene 200 block polyacrylic acid 18, by using DMF, they got sphere. But when they used THF, they got LCMS, inverted micelles. So by tuning the ratio THF-DMF, they tune the morphology between spheres, rods, then vesicles. As we said, the solubility parameters is very important. The solubility parameters of polystyrene is between 16 to 20, which is closer to THF. The solubility parameter of THF is 18, and the solubility parameter of dioxane is 20. But the solubility parameter of DMF is close to 25. So there is a huge gap between the solubility parameter of polystyrene with DMF. In other words, when the solubility parameter is close, the nanoparticle is swollen. This is why the nanoparticle is swollen in THF or DMF or dioxane, but not and it's much smaller in DMF. The NAG and the core dimension of the resultant micelles are larger in THF or dioxane than in DMF, leading to a higher degree of stretching of the core blocks. Regarding the solvent, for solvent with higher dielectric constant, such as DMF has a dielectric constant of 38.2. The ionizable polyacrylic acid blocks are partially charged. I remind you that the polyacrylic acid are negatively charged. The electrostatic repulsion in consequence, when the dielectric constant is higher, the electrostatic repulsion among the corona chains is relatively stronger. We can see here from left to right, first in the first figure. Upon increasing the ratio of water, we shift from the spherical masses which are formed at the early stage to rods, then to vesicles. And we can get different intermediate polymorph depending on the concentration of water and the water content. However, for solvent with lower dielectric constant, such as dioxane or THF, the charge on the polyacrylic acid blocks is negligible, and the repulsion among the corona chain is weaker. Reduced repulsion leads to an increase in the effective volume per corona chain on micelle surface. In summary, if the chain and the solvent have similar solubility parameter, the particle is swollen with an increased core size. However, a solvent with a higher dielectric constant, such as DMF, leads to an increase in the ionizability of the polyacrylic acid, increasing the repulsion between the corona chains, leading to higher curvature at the interfacial surface of the corona core interface, and the formation of spheres. Different composition of solvent mixture may also be employed as a versatile tool for controlling the aggregate for morphology by tuning the ratio THF-DMF. So it's possible to get from sphere, rods, lamellae, and vesicles. Addition of ions are important also to tune the morphology by using acids, bases, or salts, such as HCl, NaOH, or NaCl. HCl protonates the ionized carboxylic acid units of the polyacrylic acid, which leads to less electrostatic repulsion between the corona chains and decreasing in the effective volumes per corona chain. And it has the same effect than when decreasing the size of the polyacrylic acid chains. Therefore, the aggregates change from spheres to rods and to vesicles. I just remind you, the driving force for the control of the morphology is the repulsion between the corona chain. If the repulsion are strong, the curvature at the interface corona core is higher, leading to sphere. If it's decreased, like with ACL, it shifts from sphere to rods or even vesicles. It is the same effect with an ACL, which reduces the repulsion between the corona chains. It has the same effect than ACL. By decreasing the repulsion between the corona chains, it shifts from spheres to vesicles. By employing NaOH, it increases the degree of ionization of polyacrylic acid, leading to more repulsion among the polyacrylic acid chains and a higher curvature at the interface corona cores, leading to the formation of spheres. The addition of homopolymers increases the size of the nanoparticle. It becomes much bigger. Cross-linking leads to frozen structure by using polymer zone. A morphological transition from sphere to cylinders and to lamellae may occur as the corona forming blocks length decrease. Depending on the conditions, you can obtain kinetically trapped species or assembly under thermodynamic control. In my courses that you will find soon on Udemy, you will find all the processes to be under thermodynamic control or kinetic control or non-equilibrium. All these three processes are very important to tune the morphology and to get different polymorph. All block copolymers have a certain polydispersity because of the synthetic process. It turns out that the longer chain were preferentially segregated to the outside of the vesicles and the shorter ones to the inside. The repulsion of the polyacrylic acid chain on the outside are stronger than those on the inside, which stabilize the curvatures. For the control of the vesicle size, the percentage of water content is very important for two reasons. The first one, as a reminder, it shifts from spherical micelles, which are formed at the early stage, to rods, then to vesicles upon increase of the water content. The second effect is when the water content increases, the size of the particle increases. The vesicles are bigger. More water, bigger vesicles. As for the increase of the water content, the addition of ACL or NaCl yields larger vesicles by reducing the electrostatic repulsion among the corona chains, while adding NaOH produces smaller vesicles by increasing the electrostatic repulsion. It's worth noting that larger vesicles generally have a relatively broad size distribution, while small vesicles have a narrow one because of the interfacial area. The wall thickness of block copolymers vesicles is a function of the molecular weight of the vesicle forming copolymers. The wall thickness decrease as the size of polystyrene block polyacrylic acid vesicles decrease. Two factors may contribute to the wall thickness: the segregation of shorter corona chains to the interior of the vesicle, the decrease in wall thickness to increase the area per corona chain, relieving the anterior corona repulsion. For vesicles, freeze-thaw effects leads to indentation, stomatocyte, and fully Kippa structures. The deformation is caused by pressure difference between the interior and the exterior of vesicle during preparation. Kippa vesicles can be obtained by freeze-drying vesicle solution, then by adding water. You have the picture of the indentation, stomatocytes, and Kippa vesicles. For size hybridization, you need to keep in mind that if water addition is stopped at 7.5% content or more, because the kinetics becomes extremely slower, thermodynamic equilibrium becomes unachievable, even over a period of time of weeks. In conclusion, thermodynamic equilibrium can be observed for a range of water content between 3.5 to 7.5%, and dynamic equilibrium are observed for water content between 5 to 9% contents. Over 7.5% contents of water, the aggregates are kinetically frozen. The self-assembly process can be under thermodynamic or kinetic control. To favorize self-assembly under thermodynamic control, it's very important to add 3.5 to 7.5% of water to work with this range of water in the solution, and also to heat at a temperature higher than the TG. To be at kinetically controlled process, it's better to add over 7.5% content of water and to heat at a temperature lower than the TG. There are many other conditions to be under thermodynamic kinetic control systems. I will reveal you all the details in my courses that I will submit on Udemy. Professor Eisenberg didn't also mention in this review the non-equilibrium systems. You will have all the details about all the processes, thermodynamic, kinetic, and non-equilibrium system in my oncoming courses on Udemy. In summary, different parameters are important and have been described by Professor Eisenberg for the generation of different polymorphs. He has described 30 types of polymorphs depending on the conditions, using the polystyrene block polyacrylic acid as a model. Based on the chemical structure, the volume fraction Fa and Fb are important parameters. Indeed, when increasing the volume fraction Fa, it shifts the polymorph from sphere to rods to lamellae to vesicles to hexagonally packed hollow hoop structures until large compound micelles when Fa is closer to 1. Second parameter which is important, the process. Depending on the process, it's possible to get different polymorphs. The most popular process is nanoprecipitation, where the block copolymer polystyrene block polyacrylic acid is generally dissolved in THF, dioxane, or DMF. Then the self-assembly is generated upon addition of water. The generation of assembly depends on the water content and the time of addition. Inverting the process could lead to kinetically trapped species. The concentration effect. The aggregation number NADG increase with the number increase with the copolymer concentration, leading to the increase of the core size. Regarding the solvent content, for the water content, the increase in the water content leads to the progressive shift from sphere to rods and then to vesicles. The second effect of increasing water content is to increase the size of the vesicles as well. Two parameters are important using organic solvent: the solubility parameters and the dielectric constant. When comparing THF and DMF, the solubility parameters of polystyrene and the co-solvent are close. And in conclusion, the core is swollen. We get bigger particles. But for a solvent with a higher dielectric constant, such as DMF, it increases the ionizability of the polyacrylic acid chains and increase repulsion between corona chains, leading to a higher curvature at the interfacial surface corona core interface. You will get a bigger AC, and this increase of the curvature on the interface, it leads to the formation of spheres. It's possible to tune the shape by playing with the ratio THF-DMF. Regarding the addition of ion, HCl neutralizes the negative charge of the corona chain, polyacrylic acid, made of polyacrylic acid, leading to a decrease in the repulsion between the chains, a higher core stretching, and a lower curvature at the interface corona core, which shifts from sphere to rod to vesicles and increase the size of particles as well. NaCl. The charge shielding of the negative charge of the polyacrylic acid corona leads to a decrease in the repulsion of the polyacrylic acid chains. It's a similar effect than HCl, and it also increases the size of particles. And for NaOH, increasing the repulsion between the corona chains leads to a higher curvature at the interface corona core, leading to spheres. For the other parameters, such as adding homopolymers, the addition of homopolymers leads to swollen particles, bigger particles. For the size hybridization, keep in mind that to get a thermodynamic equilibrium, it needs time, and also it needs to work at 3.5 to 7.5% of water content. And to get dynamic equilibrium, you have to work between 5 to 9%. And we call kinetically frozen structure when upon adding 7.5% of water. Cross-linking leads to frozen structure. Freeze drying of vesicles, then addition of water, leads to Kippa vesicles with indentation, internal indentation. Thermodynamic and kinetic control process are important to get different polymorph. To observe thermodynamic equilibrium, is always better to work between 3.5 to 7.5% of water and to heat at a temperature higher than Tg. Kinetically frozen species can be obtained upon addition of 7.5% of water and by lowering the temperature below the Tg. In conclusion, Professor Adi Eisenberg has succeeded to isolate 30 different polymorphs by studying polystyrene block polyacrylic acid. He noticed 3 parameters which are important to tune the shape of the self-assembly: the degree of stretching of the core forming blocks, the interfacial tension between the micelle cores and the solvent outside the core, and the most important one is the repulsion interaction among corona forming chain. Indeed, repulsion among corona forming chain and repulsion among corona chains leads to higher curvature at the interface corona cores, leading to the formation of sphere if it occurs. But decreasing the repulsion of corona forming chain and corona chain reduce flatten the curvature at the interface corona cores. In conclusion, Professor Adi Eisenberg is typically somebody who studies in depth. All his studies are very rigorous, very focused, and he pays very attention to the details by using bottom-up approach. Professor Adi Eisenberg is a real example of rigorous study and study in depth. He has been a very important person for the understanding of the polymer chemistry and the self-assembly processes of block copolymers. In the next chapter, I will talk about the equilibrium, kinetic, and non-equilibrium systems and their effect in the complex systems. Thank you for watching.